Today we are I'm going to do more complex problem on thin wall analysis. And then after that, we are going to go into a new subtopic, which is known as longitudinal shear analysis. Okay. So the first problem that I want to go through in thin wall analysis is this one over here. Okay. So I think I posted this on Avenue to Learn. So let's look at this example over here. There's two parts of the question. Oops. Okay, so it's referring to the same structure. Okay, so this is example number 1. Okay. So the beam is suggested to a shear force of V equal to 5 kilopound force, okay, vertically. Determine the shear flow at points A and B. Okay, so you can see point A, and you can also see point B. Okay, and then the second part of the question, okay, determine the maximum shear flow in the cross section. Okay, so we're going to look into this problem. Why I picked this problem? Because this problem has more and weird, not weird, but has more terminus than any other questions that you have seen before. Okay, so there's a trend that I want you to see based on this problem. I'm trying to look for because I don't want to waste time looking for the second moment of area. I'm looking for the second moment of area values. That's why you see me a bit distracted. Okay, I think I found it. Okay, right. So we are not going to find the second moment of area. Okay, and I'm not going to waste time looking for the central also, because you all know how to do that. Okay, so if we were to label our axis, this is our y, and this is our x, and this is our z. Okay, so given izz is equal to 145.98. Okay, and then given that the geometric centroid y bar is equal to 3.709 or 6 inches. Okay, so the first thing we are also given that we have a Vy. Okay, so this is Vy, and this is equal to 5,000 pounds. Okay, this is given to us as 5,000 pounds. So we are going to look for determine the shear flow. Okay, we're going to determine the shear flow. Okay, at point A and point B. We can also determine the shear stress. Okay, so if we were to look closely, this is where point A is. Okay, and this is where point B is. Okay, so I'm going to sketch. I'm going to do a sketch, right? And we are going to sketch the shear flow. Okay, so I'm going to sketch the shear flow. So I'm just going to do so the structure look like this. then stretch itself vertically. And okay. And then we have a right. Okay. So given that this is our transformation, okay. So we firstly identify that this is our major web. Identify that this is our major web. Okay, so this is our also major web. So we design our shear flow knowing that over here, this is our Vy, and this is equal to 5,000 pounds. So the major web controls the shear flow. Okay, so it comes down. And this is okay. So this is how our shear flow has been designed. So if we look at how many terminals, we got T1, T2, T3, T4. Now, if we look at where point A is over here, this basically say that this is point A. And we look at point B, this basically look that is where point B is. Okay. So 2 or 3 weeks ago, yeah, maybe 2 weeks ago, we derive, right? We derive based on an expression. Okay, if you were to recall this diagram, right? Right, and then we have this as our geometric centroid, and then we specify that this is our Vy, right? And then remember, this is our the top dimension over here is our C, right? The bottom over here is our C also. And then we have a shear flow going down this way. And this is for whether is it thin wall or non-thin wall, the principle is the same. We call this phase our terminal, and this is our terminal. So this is our terminal 1. And this is our terminal 2. Okay. So we did derive that the shear stress is equal to V over I Q over Z, right? And we had a relationship. I can't really remember. I think we derived that the shear stress is 3 over 2 V over A bracket 1 minus Y squared over C squared. Okay, we derived that. Okay. So one thing to watch for, why I draw this, because this is the where we derive our formula, and there's a certain trend that we have to follow. Okay, and I want you to observe this. Okay, now first thing first. Okay, to find the shear flow, the formula that we're gonna use is pretty straightforward. So Q is equal to V over I multiplied by Q. And we know that this is for thin wall analysis. Here we have thin wall. And we know that shear stress, shear flow is equal to VQ over I. Okay. And what we also know is V and I are what? Constant. Okay. So if you look at point A, okay, if we were to focus on point A, right? If we were to focus from point A, the terminal is at T1, right? Why at T1? Two things. Because it is the closest, okay, and also direction is the same as T1, right? So what I mean by that, at point A, right, you see that it's flowing in a what? In a horizontal direction, okay? So we also know at point A, we have to apply a box beam, okay, box beam analysis. And this is because we have one terminal and two arrows, right? One Q go to one side, one Q go to the other side, okay? For this case, we know we need 2Q, okay? So when it's 2Q, the area that we are going to analyze is this whole area over here. Okay, this is the area that we're going to analyze, okay? So the first moment of area at point A, okay? So I'm going to take this image now, and we can see better, right? So QZ at point A. So remember the area that I told you that we're going to look at. So it's this whole area over here, right? This whole area over here. So we know the width. The width is going to 5, 10, 0.5, 0.5. The width is 11. The depth is 0.5. And the Y bar is equal to, we are given the centroid from the top is 3.70946. Okay, let me go through it again. 3.70946 minus by 0.5 divided by 2, right? So this will be equal to 0.5, 3.70946 minus 1.5 divided by 2 times by 0.5 times by 11. It's equal to 1919.027 inches to the cube. Let me do it again. Right. Okay. So it is correct. So from here, QZ at point A, or the shear stress, QZ small q shear flow, okay, at point A is equal to V. So V over here is 5,000. Q 19.027 divided by second moment of area I, which is equal to I wrote the I back, 145.98, and 2 because of what? Box B. Okay. So this will be equal to 5,000 multiply 19.027 divided by 145.9.